Good evening, folks. My name is Mark Razzie from JPL's Office of Communications and Education, and it is my absolute pleasure to be your host for this edition of the Von Karman series. Today, we're going to be talking about the upcoming SPHEREx mission, which is a medium explorer satellite telescope that aims to produce the first ever all-sky spectral survey. Every 6 months, SPHEREx will survey and create a map of the entire sky in 102 color bands, far exceeding the color resolution of previous all-sky surveys. This data will then be used to help answer questions about how galaxies and the universe began. So to help handle the myriad questions we hope to get from all of you tonight, let me introduce our co-host today, Public Outreach Specialist and Universe Public Engagement Lead, Caitlin Soares. Hi, Caitlin. How are you?
Hey, Mark, doing well tonight, and hello, everyone. Thank you for joining us. So just a reminder, as Mark said, that you can leave questions in the chat or in the comments tonight while you're watching, and we'll have a little bit of time after the talk for Q&A. We're really excited for this one.
Oh, thanks, Caitlin. Yeah, this should be a good one tonight. So to lead us along tonight, we actually have a very special guest from his office at Caltech, the principal investigator of SPHEREx. This is his baby, Dr. Jamie Bach. Jamie, thank you so much for making time and for joining us today.
Hi, everybody. It's a pleasure to be here. SPHEREx is coming along. Our project is really in a busy phase here, and I hope I can convey a little bit of our excitement about that and the science that we're going to do when we get up into orbit.
Excellent, excellent. We'll have to revisit this once we start getting some data back too. So first of all, let's talk about the title of this talk. It's a little different than one might expect knowing the spacecraft is a telescope.
Right. Yeah, we think of telescopes as, zooming in and seeing some object that we couldn't possibly see otherwise. So I took that notion and kind of turned it on its head for SPHEREx, because the thing that makes SPHEREx unique is really covering the whole sky and doing this in a bunch of color bands, doing it in spectroscopy. And so really we are seeing the big picture view. We're seeing the whole sky. And another thing is our science covers such a sweep here that when I'm talking about it, we're going to zoom out from our own local solar system all the way out to the edge of the observable universe, which is really the big picture. So that's the reason for the title.
Okay, that works. So how's this thing actually work? Let's talk about that.
Yeah, so if you go to the little animation here, this is SPHEREx as we hoped it will be about a year from now. Obviously, we're in low Earth orbit, and the key thing about SPHEREx is we observe at infrared wavelengths. So these are wavelengths just a little bit longer than your eye can see, out to 5 microns, which is about 7 times longer than the longest wavelength your eyes can see. And in the infrared, you're sensitive to heat. And so the first thing we need to do is we need to keep the telescope cold and the detectors cold. And that's a challenge being here in low Earth orbit, because got the warm Earth below us and the sun off to the side. So you saw those big kind of martini glass shaped cones on top that just disappeared. That protects our cold telescope and detectors from all that heat radiation from the Earth and from the sun. And actually, we cool the whole instrument by radiating heat out to cold space. And by doing that, we can get the telescope and detectors to a very low temperature without any other kinds of active cooling, just by the natural cooling to space. The other thing you can see is we have a small telescope. It's that black thing sticking up towards the sky there. The telescope is small, but don't let the small size fool you, because it has an enormous field of view, which means it can collect a lot of light in spite of its small size. And that light collecting power is really key to mapping the whole sky. You have to have enough observing sensitivity in order to do that. And then the next thing is we're doing spectroscopy. We break the light up into a bunch of different color bands. And the way that happens is also unique. So what I have here is one of the spectrometers, or really a filter that we use to do this function. And so it's in the infrared, so you can't see through it with your eye. But at every point on this filter, it forms, it lets in a certain wavelength of light, and that wavelength gradually shifts as I go along the filter. We place this filter right over the detectors. This is kind of a new idea in astronomy. And so if you go to the next slide, you can see how this process works. We've actually got 6 detectors and 6 filters. And when we observe a source, that source lands on one wavelength. Actually, it lands at 2 wavelengths because we split into 2 focal planes, a short band and a long band. And so that tells us 1 wavelength, and different parts of the sky are, in the meantime, getting observed by at other wavelengths. So in order to get a complete spectrum, we need to take a bunch of exposures. And so what this little animation shows you is, if you imagine an object, we take a series of snapshots, and each snapshot's about 2 minutes. So this is greatly sped up. And by taking 51 different snapshots of that object, as it moves along, we get a complete spectrum. So you see the spectrum being filled out there on the bottom as we take this series of exposures. And so that's basically the idea. The good side is that this is really simple. The spectrometer is just a filter. It's super light and compact. The downside is we need a bunch of exposures in order to, observe the whole sky or observe anything we want to do. If you go to the next slide, you can see how that works. So we've got to cover the whole sky at all these wavelengths. And because, again, we're infrared, we have to avoid seeing the Earth or the sun. So that leaves us a little semicircle of sky that at any moment we can go off and observe. And so what you see here is a series of exposures, and each of these, again, is about 2 minutes. And we get 4 or 5 of these. But since we're going around the Earth, and we're going around from North Pole to South Pole, basically, after a while, the Earth rises up and we get too close to the Earth, so we have to move the spacecraft and observe at a new patch. So each of these patches gets, of order 4 or 5 observations, and then we got to scoot on over and do a new patch. And so this whole collection of images is kind of like a giant puzzle. We have to put it all together if we want to see an object, at all the wavelengths, which is what we want to do. Yeah, so if you go to the next animation, now this is really sped up. Okay, this shows, again, each of these exposures were 2 minutes. We're going around the Earth about every 95 minutes. So yeah, this is really on fast forward. But it's showing how we're mapping the celestial sphere. And when it turns gray, that means we've got complete spectra for that region. And so the sphere here is gradually filling in. And then over 6 months, we've completed the entire sphere. And we have one full map where we've got a spectrum for every piece of the sky, everywhere we point. And then the baseline mission lasts for 2 years. So we actually get 4 of those all sky surveys at the end of our baseline mission. Then, so at the end of our baseline mission, the next slide here shows, we're going to have an incredibly rich data set. It's the first data set really of its kind, where we have a low resolution infrared spectrum for every pixel on the sky. And that's never been done before in astronomy. And so it's going to be very interesting. There's a lot of discovery every time you take a new kind of measurement. And so we're anticipating science that goes from our own solar system, with studying the spectra of comets and asteroids, and maybe that bears on the assembly history of our solar system, all the way out to hundreds of millions of stars, hundreds of millions of galaxies, and even exotic objects like quasars, which are massive black holes in galaxies, all the way out at the edge of the universe. Also, this data comes out to the public on a rapid timescale, and the history of these missions is actually that a lot of the science, even most of the science, is actually done by the public mining through the data on their own. Of course, we have some directed ideas what we want to do as well.
That is a lot of data. I'm sure you have some crazy terabytes number for how much you're going to be getting back. So I guess my question is, like, how does this all fit together? And then, as we had talked about before, we were sort of putting this together, what specific investigations are you hoping to get from this data?
Yeah, right. So, the first part is really just this survey, of course, just making it available and standing back and watching what the community comes up with. But we do have some science themes of our own that we really are focused on. And this gets to the zooming out part of my talk. So let's get oriented and go to the next slide. So let's start with our sun and our own place in the universe here. And yeah, the universe is a really big place, and we can think of the size of the universe in how long it takes light to travel from some object to us. And so the sun is, you think, fairly close on a cosmological scale, but it actually takes light 8 minutes to travel from the surface of the sun to us. So we're also seeing the surface of the sun as it was about 8 minutes ago, not now, because of the light travel time. This is kind of annoying in the solar system, but as we go further, becomes kind of a feature. The next nearest star is actually about 4 light years away, and that's a tremendous distance if you're talking about sending a robot or a person to that star. It's way beyond our current capabilities, but it's right around the corner in terms of our galaxy and the size of the universe. And then one of the themes we're interested in is studying how stars, the process of star formation. So one of the famous regions of star formation, one of the closer ones, in fact, is the Orion Nebula. And it's at a distance of about 1,300 light years. Okay, so again, getting further, and we're seeing that light from the Orion Nebula more than 1,000 years ago from when it was emitted. And then the next object is our Milky Way. And here, you can see the Milky Way on a dark night. And the center of the Milky Way is about 27,000 light years away. The interesting thing is you can see the bulge and pattern of the Milky Way with your eyes, but you can't actually really see the center. And the reason for that is that you see those clouds of dust. That's obscuring the center of our galaxy. And so looking in the infrared, it's easier to see through that material. And that material also is where stars are being born. So this leads us to our first theme. If you go to the next slide, that stars are born from these, by astronomical standards, dense clouds of gas and dust. And our first investigation is, what were the conditions for life to form in these forming systems outside the solar system? And at least on Earth, life is associated with liquid water. We can ask, where did that water come from? And that water actually was formed in the interstellar medium, and it's locked in a form of ice, not water vapor or water liquid. The ice is really stuck on the surfaces of dust grains. And so to understand how that water got to Earth, or how abundant it is for a new system, to follow that water, we really want to actually follow the ice itself. Ice is not actually that well studied in astronomy. Again, people have zoomed in on particular regions with powerful telescopes. What we do with SPHEREx, if you click the animation, is we use a background star, and by looking at the spectra of that star, if you click, there's distinctive features from the materials that are sitting on the surfaces of these dust grains. It's really kind of like a fingerprint. And so you can see there's a strong feature from water ice, but there's other materials as well, organics, interestingly enough. So there's carbon dioxide, carbon monoxide, methanol, and some other things. And the depth of those features tell us the abundance of those materials. And that's really interesting, of course, because they're key to life. And with SPHEREx, we're not studying a few objects, we're getting the big picture. And so instead, we're going to study the amount of ice in all the early phases of star formation, going from dense clouds, which then gravitationally collapse to start stars and planetary systems, through those early phases, and then even to phases where young planetary systems are starting to be born out of the material, called a protoplanetary disk. And we believe, from mapping the whole sky, we're going to have millions of such high quality observations. So that's really a game changer for this kind of science.
That's awesome. How far out you think you're planning to go with this, distant wise?
Well, let's keep going on our journey. Yeah, so if you look at the next slide, we're going to start zooming out more here. And so we talked about our galaxy. Well, our galaxy's surrounded by some small galaxies that are orbiting it. So a couple of examples of those are called the Magellanic Clouds. And those Magellanic Clouds are about 160,000 light years away, so starting to get pretty far. And then there's a famous large galaxy similar to our own called Andromeda, and it's 2.5 million light years away. Again, so now we're seeing objects as they were millions of years ago. And well, let's keep zooming here. So yeah, so this is I apologize for the 1980s graphics, but I think this shows a nice layout of where objects are in our what's called our local group. So you see our galaxy, you see Andromeda, lots of dwarfs galaxies, and the scale bar here is 1 million light years. Okay, so that's kind of our little neighborhood of galaxies, and now we're going to zoom out another factor of 10. Yeah, so this is a theme in astrophysics where, if you think you're special or unique, you find out you're not. And so, not only is our local group not the only group, it's not even a very big group. If we zoom out a factor of 10, we start to see galaxies in clusters, clusters that are much bigger than our own, as well as places where there aren't galaxies, interestingly enough. And then let's zoom out another factor of 10. And here you can see now, not only are there clusters of galaxies, there are these kind of big walls of rich regions where galaxies are abundant, and voids where galaxies are very scarce. And now the scale bar here is 100 million light years. And then let's go out one more slide. Yeah. So now this is another factor of 10. And so the scale bar is 1 billion light years. And I have to say a couple things about this picture. The first is that unlike the other pictures where we have objects have names and we've measured them, we're still working on this picture. This is not entirely known. These objects are, we've only mapped out part of this. And mapping this kind of structure out further is definitely one of the big themes here with SPHEREx. The other thing to say about this picture is, boy, 1 billion light years, right? That little scale bar. And this picture is showing where galaxies would be. The universe is about 14 billion years old. So the edge of this image is kind of the observable universe. That's as far back as we can see. And what's missing here is this image is plotting objects, but because of the immense distance, it's not really describing the notion of time. And so for every one of those ticks every billion years, we're seeing those objects as they were billions of years ago. And even for a galaxy, that's a long time. So if we look for those ticks back 4 billion years, we're seeing light that was produced before the Earth existed. And the further we look with galaxies, we find that they don't look the same as galaxies today. They're different. And if we go back further and further, eventually we actually get to a time where there were no galaxies. So that's because the universe had a beginning and has been evolving, and it takes that light travel time to get to us. So as astronomers, we also get to be historians and understand this history. And so this gets to our second theme of, how did all this galaxy formation happen over time? And if you go to the next slide, this shows the time axis. So we live in an expanding universe. Started with the Big Bang, and the further we go back, the hotter and denser the universe gets. I mentioned this period where we can see back to a time where there were no galaxies, and the universe was just filled with a glow that's now in the microwaves. That's the cosmic microwave background. And from that medium, this is the time when the universe transitioned from free electrons and protons to neutral material like hydrogen and helium. From that material, somehow, galaxies formed and ignited, stars ignited. That period of time is called the Epoch of Reionization, some 500 million years or so after the Big Bang. And we know, roughly speaking, how this picture looks. Galaxy formation started picking up, and actually it peaked about 5 billion years after the Big Bang, and it's been on a slow decline ever since. Now, the way most astronomers study this and the way we know what we know today about galaxies is by taking large telescopes and zooming in and looking at the properties of individual objects. With SPHEREx, we're a small telescope, and we want to understand how galaxies began and formed and the history of galaxy formation. But we're going to do this in a really new way, and that's to study the glow, the total glow from all the galaxies. So we're not looking for the individual objects, we're looking for the aggregate glow. This is the light that galaxies produced over time, and understand how that light was produced going back from those early moments when first stars were forming all the way through this peak of star formation to today. It's called the extragalactic background light. And if we can detect that glow, it can tell us about the galaxy formation process writ large, how it happened on a cosmological scale. Right. So if you go to the next slide, this is a hard measurement to do, unfortunately. And so what makes it challenging is that our sky, even when from space, is pretty bright. And so you see here a picture of two kinds of foregrounds. And the foreground on the left is the galaxy. And the foreground on the right, maybe some of our listeners will know what it is, but a lot may not. It's due to something called the zodiacal light. And it's basically our solar system is glowing. And the reason it is there's some dust in our solar system, and sunlight scatters off those dust grains and makes the sky luminous. And so if you're at a dark place right after sunset, you might see this kind of triangle of light from the zodiacal light. It's a fascinating topic. For us, it's a giant weed, however. And the problem is that the sky is many times brighter than the signal, this glow from galaxies that we're looking for. So people have tried, including myself, to heroically remove, the local glow to look for the light from galaxies. But we're going to use a new method. So if you go to the next slide, this is actually data taken by a satellite at longer wavelengths in the infrared. And it's a patch of sky with, out basically blank sky here, but a large patch. You can see the size of the moon. And the resolution, angular resolution, isn't that good. So most places in this map, you can't say if there's one galaxy or 3 or 7. A couple places you can see bright objects, and those are distinct, individual objects. But most of the map, you can't tell that. But what you do see, if you step back and look at it, is you can see this kind of quilted pattern. And that's due to the fact that galaxies are clustered together. And so this observation really leads into the method we're going to use with SPHEREx. If you go to the next slide. So this is basically the way it works. What you see here is a simulation of galaxies forming. And if I had a big telescope, I would zoom in and I would measure the individual galaxies and their properties and study galaxy formation that way from those objects. But the thing is that my data set, if you go to the click through, consists of only those objects. Instead, what we're going to do with SPHEREx with our small telescope is actually just look at the map itself. And we use the fact that it has this distinctive clustering pattern because galaxies cluster together, whereas the foregrounds are very smooth. We know that. And so just the map itself is a measure of the aggregate emission from galaxies. And the cool thing is it tracks emission from everything, from big galaxies that we can detect to little dwarf galaxies that are really hard and challenging, to maybe even fuzzy stuff from, the fuzzy peripheries of galaxies. It measures it all. As long as whatever it is that's emitting feels the force of gravity and clusters together, that goes into the measurement that we make. This has been done. You saw the maps presented, but the key thing here again is spectroscopy. So we can now take this map and break it apart into its constituent colors. We've got 102 of those bands. And that's really key because what we need to do is we need to invert this history. And so doing that spectroscopy allows us to tease apart the history slice by slice as we go back in cosmic time, and hopefully even detect the fingerprints of these first era of galaxy formation when galaxies were just turning on.
Wow.
Yeah.
That's pretty cool. I mean, I love the fact that we can actually see them clustering together in some of those images. Do we know why they do that?
Yeah. So that's an interesting question. If we go to the next slide, where we go back to this picture we had, galaxies cluster together, and why is that? And to answer that, I have a little bit of a numerical simulation which shows how galaxies and how this structure that you see, this large scale structure, how that forms over cosmological time. And I have to say, introduce this video. It goes by pretty quickly. So first thing is there's a timer, and that's going to tell you the time since the Big Bang. Okay, so we're going to start from early times and go forward. So you see that timer, and that's in billions of years. And what you see is an initial kind of structure, and it gets more defined and brighter. Also, the scale here is a small chunk, about 500 million light years on a side. And so here's the interesting thing. If you look on small scales, you can see that there's a lot going on. Galaxies feel the force of gravity from their neighboring galaxy, and they move in response to that. But if you look on large scales, you see a little bit of flexing perhaps in this structure, but on the large scales, that structure was already there. Galaxies may feel the force of gravity or whatever, but 14 billion years is just not enough time for them to appreciably move. They can move a little bit, and that's why that structure gets more defined into this kind of webby structure we see here. But that initial structure was already there. So something set that up. And that gets to our final theme here. So if you go to the next slide, this is by way of explanation for what happens. That structure was imprinted in the universe from the Big Bang. And so if we go all the way to the left here, at the very moments after the Big Bang, there's this period of time called inflation. And this is a hypothetical expansion of the universe happening at very early times. And as we go back in time, the universe gets hotter and denser. At this very early time, the universe was at incredible temperatures and energies. And this inflation, you're not going to believe it, but those large scale structures that we see, those walls and voids, began as quantum mechanical noise. And that quantum mechanical noise, according to the theory of inflation, was expanded to enormous scales and imprinted these fluctuations on the universe. And then, when stars and galaxies turned on, they followed this structure that was already there. And that's what that movie was basically showing us. The really exciting thing about that is that means that the fingerprints of inflation are with us today. They form this structure. And so we can say more about the birth of the universe by studying that large scale structure. And I wanted to say a couple things about inflation itself. So inflation is an idea that came about 40 years ago. And the idea is that the universe went through this expansionary phase. And there's nothing in the laws of nature that say that that can't happen, but it definitely requires some exotic process, some process that we don't know about. We don't know the physics that would produce it, but there are many possibilities, okay? And in those 40 years since this idea came along, experimentalists like myself have been working really hard to test this notion. And every test that we do is consistent with the basic idea that inflation happened. And so now we really want to know, what is this stuff? How did it come about? And that's also a challenge because at these early times, we're at energies where we don't really know the laws of physics. It's beyond the energies that we can measure with like particle accelerators here on Earth. So if we really want to understand more about inflation, the universe is our best laboratory. So what SPHEREx is going to do is it's going to map out that large scale structure that we saw. And the distribution of that structure is sensitive to inflation. And so we can take that measurement and work backwards and say something more about this exotic physics that caused this expansion really associated with the Big Bang itself.
That's amazing. Yeah, that data is going to be amazing. It's the knowledge we learn from like trying to understand how that structure started, and it's all a result of that kind of initial pop, as it were, right?
That's the idea, yes.
Wow, just the way that all may have randomly sort of formed. So,
well, it was a long time ago, but it was a really big event. So, but it shouldn't be too surprising that we still see traces of it.
Yeah, for sure. It kind of defined everything, didn't it? So I guess my next question then, so that's kind of a science, that's pretty amazing science overview, needless to say. How's the hardware coming along, and when do we expect to launch?
Right. So I'm a hardware person myself. I love hardware, and I love building things. So I have some pictures of the the experiment being assembled here. So we can just click through these quickly here. So the first here, this is the cone shields. We are a bit nerdy, so we call them photon shields in reference to Star Trek. They protect us from photons from the Earth and from the sun. There's actually 3 of them nested together here, and there's a human for scale. They're a bit taller than a person, and if you go to the next slide.
Those are the aforementioned martini glasses, correct?
These are the aforementioned triple martini glasses. That's right. And so this is a vibration test. So this is one of the terrifying things we do, is to show our hardware works. We put it through environments that simulate launch. So here we're sweeping the frequencies up on a vibration table. And if you've ever seen one of these tests, this test is particularly frightening. And you can see as we go up in frequency now, the inner shield's really starting to vibrate.
Yeah, that makes me nervous just watching that.
It makes me nervous. You can see that the guys in the background there are just totally blasé. Like, yep, that's supposed to happen. And it is. And so, we actually passed this test. It was supposed to do that. We've passed this test with flying colors.
Excellent.
Yeah, if you go to the next slide. This is our telescope, and it was produced at Ball Aerospace, now British Aerospace. It's a lovely thing. And so this is just showing the entrance there. I can't see the mirrors. And then the outputs go to the detectors. A beautiful piece of hardware. You'll notice it's all painted black, and that's because we want it to radiate heat out to to outer space to help keep it cold. Go to the next slide. So when we're testing the instrument, we have to simulate the environments of space. We have to keep the whole thing cold and in vacuum. And so we have a special chamber that allows us to do it. This is actually half of it. And it was shipped from Korea by our collaborators. It's really performed amazingly well. And we had to install it in the basement of the Cahill building down here at Caltech. And there's no elevator that's large enough to accommodate it, but fortunately the designers of the building had thought of this. And so there's doors, well, actually they're just plates of concrete that can be lifted up out of the parking lot and enter into a basement laboratory. It's called the crypt. And actually this is the first use of the crypt, where there's a piece of equipment that's large enough that we had to use it. Actually, this is half the chamber. There's another piece that's about this size. And so for about the past year, we've been doing test after test with putting the instrument in this chamber and putting it through its paces. Go to the next slide. This is just a picture of the telescope. And again, you can see the extreme care and baffling we have to reject sources of light that are coming from off axis. It's a kind of beautiful thing, I think.
That's a great shot. This gets right out of some sci-fi picture.
Right. Yeah, next slide, please. And we have a team of people working in the basement tirelessly. Each of these runs is a long, kind of a marathon of weeks, or the last test was a couple months. And they're a fun group of people, as you can kind of tell. We do some of these measurements in the dark. So this is one of the young scientists, postdocs, Gene Wen, who's been measuring the performance of the instrument. Go to the next slide. And then you saw the vibration test of the shields. This is the vibration test of the assembled instrument. So this is a telescope, detectors. It's got the bottom part of the cooling system, and it's getting the same treatment here. We've got everything in focus, and now we're going to shake it to simulate the launch vibrations and see if it comes back in focus. The masked person in front there is actually the director of JPL, Lori Lesher.
Excellent.
Next slide. And these people are smiling because we've now returned the telescope back to Caltech, and we've done another focus test. And lo and behold, everything's in focus and working. So that
Yay.
was obviously a big milestone.
That's a big
Next
win.
slide. Yeah. And we like to have fun. So here's people hard at work in the lab with a visitor. That's actually our project manager. This is for Halloween. It's a great outfit. And everyone's having a good time. And finally, we are getting ready here with SPHEREx to launch early 2025, hopefully about a year from now. And in fact, today was a big day for our project, because after testing this instrument in the laboratory for basically about the past year, we just today put it in a truck and shipped it off to Boulder, Colorado to be integrated with the spacecraft. And hopefully we're not going to see it coming back. And that's a huge milestone here for our project.
Yeah, congratulations. That's a big one indeed. It's just like sending your little child off into the world there, for sure.
It's like going to college, I think. Yes. We'll see how they do.
Right. Cross your fingers, hope for the best. And hope you raised it well, right? So with that all being said, I think this is actually a really good time, since we've talked about the hardware and a little bit of the science. Let's go to Caitlin. Caitlin, how are the cues coming out there?
We have a lot of great questions coming in. The first ones directed to you, Jamie, are about the orbital placement of SPHEREx. So could you talk a little bit more? Donald Miller and Arvel on YouTube and LinkedIn, respectively, are asking, why isn't SPHEREx placed at L2 like the James Webb Space Telescope? Why was low Earth orbit chosen?
Right. Great question. We asked that question as well. So I'll just say our orbit in low Earth orbit is so-called terminator orbit. So we're flying basically over the sunrise-sunset line. And this has been used on similar missions. It allows us to keep the sun at 90 degrees off axis and the Earth always below us. We would love to be at L2. And so part of the issue here is we're mid-X, a medium explorer. So we're cost constrained. And that means we have to have a strategy that fits within the cost allocation. And so we looked at L2 as a place to go. It's clearly a better place for us. We wouldn't have this problem with the Earth always coming up. And we wouldn't have a problem with, low Earth orbits getting very busy with satellites. We wouldn't have that problem either. Unfortunately, it just wouldn't fit within our cost box. And so, we have to make tough choices. And I think it's good overall because, this is a unique opportunity as long as we can, stay disciplined. And so that's the reason.
We have a follow-up to that question as well. So you mentioned other satellites in low Earth orbit. Are other satellites a problem for SPHEREx at this level? Are you foreseeing any issues?
They are a minor problem, yes. So we anticipate our field of view is really big here. It's about 40 square degrees. And according to current estimates, we expect to see a satellite streak in basically every exposure. But the size of the streak and the number of pixels we lose is pretty small. So not happy about it, but think it's acceptable. And because we have multiple sky maps, we can fill in any patches that might get, contaminated.
Gotcha. Thank you for those. And our friend Whitney Clavin on YouTube is asking a little bit about the science. So could you tell us more about what specific questions about inflation that SPHEREx will address?
Right. So with inflation, as I said, the physics of it is not really well known. So it's kind of a playground for theoretical scientists. They can dream up many different possibilities for how inflation might have transpired or some other mechanism. So there's hundreds of theories of inflation, in fact, but they fall in general categories. The kind of effect that we're looking for is basically the distribution of fluctuations. Those are the seeds that form this large scale structure. And if those distributions have like tails, then, or so-called non-Gaussian tails, those tails are rich regions for either forming galaxies or not forming them. And that is the kind of effect that we would see with our observations. The way you get these in general is if inflation is governed by more than one field. And so with SPHEREx, it's separating whether inflation was caused by a single field or by multiple fields. That's really what we can get at.
Fascinating. Thanks. So Dutch E on YouTube is asking, you mentioned that the SPHEREx mission will be a 2-year mission. What is the actual expected lifetime for the hardware, the spacecraft itself? Might it be used past that 2-year time frame?
Right, great question. So there's nothing, we have no expendable on SPHEREx. We don't have any propellant, we don't have any coolant. And so it's the life of the hardware, first of all, which should be long, I hope. The one thing that we know about, which will eventually end the mission, is the orbit is chosen. This is a rule such that the orbit decays after 25 years. And so at that time, SPHEREx will eventually, the orbit will decay and will come back and burn up in the atmosphere. But 25 years is a long time. So yeah, NASA willing, we can keep observing past our baseline mission, yeah.
Fingers crossed for that one. I think we also have a teacher here, or maybe a student. So Kimberly is on LinkedIn, and she's asking, well, she's saying, I love this, Google Maps for the universe. Will this be available for use in the classroom with students?
Well, I can say that our data is available very quickly. Whether, how you access it for a teaching experience, I guess we'd have to talk about that. But we do make the data available to everybody. And there'll be some tools where you can look at it and do things with the data. There's quite a lot of it, however, so might be a challenge to present. We do plan some tools that'll help visualize, and one of the challenges we have is these are really three-dimensional things, right? Because you see the two-dimensional image, but then we've got the spectral direction, the wavelength direction. So visualizing that is kind of a challenge, but that's really the new exciting thing about SPHEREx.
Great, thank you. Yeah, open data is incredible. And then Casey on LinkedIn, we have one here from her. Do you expect to observe change in astronomical objects over the 2 years that SPHEREx will be observing the sky?
Yeah, that's another great question. So there's a whole field in astronomy now for looking for transient events, and we're not really designed to do that, but we can help. And so one thing we can do is we can establish a baseline, and then if transients are discovered, somewhere, we can come back and see in our next survey what happened to that object. Did it get brighter? Did its spectrum change? In some places on the sky, we have fairly rapid survey capability. So, I mentioned that we're going over the poles of the Earth. That means that the poles we actually cross multiple times. So we observe those regions pretty routinely. Regions more at the equator, not so much, more like every 6 months. So, I think it's going to be a bit of getting lucky and using our data as a baseline to see, certain kinds of transients and certainly any kind of long-term behavior, like star systems that are going through a bombardment phase, for example. We know some of those. SPHEREx will be obviously really good for those kinds of events too.
Great, thank you. This is another interesting question about other NASA missions. So Brad on LinkedIn says, being able to see the whole sky versus picking one small focal area will be incredible. I think the follow-up question here is, what complementary missions will be able to use SPHEREx's data in their observations?
Right. Yeah, so complementarity is great, and we have a lot of it. I'll just give you a couple of examples. So one is James Webb. That's a huge telescope, doing really well, doing amazing stuff. And for a lot of our themes, Webb can zoom in on particular objects. So I mentioned like studying ices. Webb has much better sensitivity and spectral resolution than we do, but we have millions of objects. So, you can take a few of those objects that are the most interesting from SPHEREx data and then go and really study them well with Webb. Another example is there's a European mission with NASA participation called Euclid, and there's another one coming that's a NASA mission called Roman that's doing similar things, mapping out galaxies in 3 dimensions in different ways. And so the combination of the data sets there open new possibilities, allow cross checks. They're actually focused on a different property of the universe, not inflation, but the fact that the universe now is expanding more rapidly. It's accelerating by something mysterious force called dark energy. The combination of these data sets is always more powerful than any one by itself.
Great, thank you. I think we have time for one more question. We have one from Wildcard Adventures on YouTube who is asking, how will spectroscopy be able to differentiate? I'm sorry, let me go back. Wrong question. Will spectroscopy be used on the moon as well as Mars? I guess, is ground-based spectroscopy on our planet or other planets or satellites possible versus, the space-based version?
Right, sure. So, yes, astronomers use spectroscopy all the time, and but mostly from the Earth, and the surface of the Earth, the atmosphere of the Earth, lets in some wavelengths better than others. So in the visible, it's pretty good. As you go out into the infrared, the atmosphere gets more and more absorptive and also glowing, as well as the telescope glowing. So as you go to longer wavelengths, space becomes a larger and larger advantage. So, part of the reason we're at the infrared wavelengths is to make use of those advantages, given our, access to space and those wavelengths. You can observe some of them from the Earth, but it's pretty challenging.
Thank you, Jamie. These were great answers. We had so many good questions. But I'm going to throw it back to Mark as we're a little low on time, and we'll try to get those answered in the comments and in the chat before we go. Back to you, Mark.
Very good. Thank you so much. Well, folks, that is indeed all the time we've got tonight. So I want to thank Jamie. You did a great job tonight. Thank you for putting all that time and effort into this talk for us. Caitlin,
yeah, my pleasure.
Thank you.
I love SPHEREx and glad to share the excitement. We're really looking forward to getting up there about a year from now.
Yeah, this is definitely one we're all going to follow along with, that's for sure. Caitlin, thank you again. Wonderful job. Social media team, audiovisual folks, thank you all for your work tonight. And of course, all of you, thanks for tuning in to join us for this show. This will be available on YouTube later if you want to go back and revisit. Please be sure to join us next month. Lecture next month is going to be cool. It's going to be about the Ingenuity helicopter, which is the first thing to fly on another planet. If you're not familiar with her, I encourage you to look it up. It's been a spectacular mission. And of course, remember, this is your space program. So, be involved and stay curious. Thanks again for tuning in, everybody. Have a great night. Good night.